to switch. Thank you, Martina, for stopping sharing your screen. We have to switch to our second speaker of the day, which is Simone Virili, and is gonna talk us about factorization systems on derivators. Simone, whenever you feel like, you can share your screen.
Okay, let's see. Do you see it?
Yes, I do.
Okay. So thank you for the invitation, especially to Fosco that insisted a lot for me to give a talk here. And yeah, I will talk today about a long ongoing project we have with Fosco. We started, I guess, like 5 or 6 years ago. Already a couple of papers have been published about this, but this is still the ongoing basic structure of factorization systems on derivators that we started with, and that it is still going through a process of big revision, and we hope we will submit it soon. So I will start with a brief introduction about factorization systems that you probably all know, but it is mostly to fix conventions and just to let you know what is my focus on that. And then we will go to derivators and see how to extend things there. So take just the category C, any category, and the pair of classes of morphisms in C. And then you say that that is a factorization system. If, well, the morphisms from one class are orthogonal to those of the other class, which just means that whenever you have a morphism in the category of morphisms, so a commutative square, there is a unique diagonal that fills the square. And you want that these two classes are maximal with respect to this orthogonality relation. And then you ask that any morphism in the category can be written as a composition of a morphism from the first class, followed by a morphism in the second class. So there are lots of examples. Here I give you 2 examples I am interested in. So if you take an abelian category A, then if you take the class of all epimorphisms and the class of all monomorphisms, then this is a factorization systems. And another example, almost an example, is, well, for any category C, you can take a reflective subcategory C prime and take the reflector. Then you can define a class of morphisms to be the class of morphisms M to be just those morphisms that become invertible in after being reflected. Then if you take this pair of the class M and its left orthogonal, then this is always a prefactorization system in the sense that the two classes are orthogonal and they are maximal with respect to this relation. But you don't know in general if every morphism can be written as a composition of the two classes. But if C is an abelian category and C prime is what is called a torsion-free class in the sense of Dixon torsion pairs, then this is always a very special factorization system. So this is the, for example, one of my objectives when I started working with these things in derivators was to take this example and see what the analogous for, say, T structures in a triangulated category should be, just viewing T structures as a parallel to torsion pairs in abelian categories. So we have this definition, the first examples, and some basic properties that we will want to reproduce for any candidate of a notion of factorization system in derivators. So the first property is that, well, things that are orthogonal to themselves are just isomorphisms. Then that the two classes should be closed under retracts in the category of morphisms. well, closures under limits and colimits, and some cancellation properties that comes for free. For example, for the class E, if you have a composition of morphisms that is in there, and the first one of the two of the composition is in there, then the other has to be as well, and you have a dual cancellation property for M. And finally, if you take any morphism in the category and you write it as a factorization with respect to our factorization system, then the maps you get are not arbitrary, but in fact they are unique up to isomorphism, actually up to a unique isomorphism. And in fact, the choices of these two maps are functorial. And more precisely, you can say that the class E is a correflection of the category of arrows, and the class M is a reflection of the category of arrows. But you can say it even better in the sense that you can equivalently describe a factorization system as a functor that goes from the category of arrows to the category C, and that with the property that sends, well, morphisms that are identities to the object of which they are the identity. So just to make clear the connection, do you see this triangle here? The functor f would send this small map f to this vertex in the middle. Okay, so to summarize this and to put it in precise terms, you can say that factorization systems can be equivalently described as suitably defined. I will not be entered in details here, but as Eilenberg-Moore algebras for the squaring monad on the two category of all categories. And the squaring monad is just the monad that sends a category to its category of morphisms, category of arrows. So, okay, so this is the aspects of factorization systems I want to extend to derivators. And yeah, as I said, this is a joint project with Foscolo-Reggiani. Okay, so the structure of the talk will be more or less the following. We will start with some setting, by which I mean I will recall you some partial definitions, cheating a little bit about derivators and stable derivators and so on. Then I will propose you a first definition of factorization system in a derivator. Then I will show you a second, a bit more restrictive definition. And then we will specialize to the class of stable derivators, where both notions coincide and where we can actually find the strongest results. Okay, so let's start with a little bit of derivators. So let's fix some notation. I will denote by this small cat the two category of small categories, and by this big cat the two category of all categories. Of course, if you take this literally, there are some theoretical problems, but I think none of you will be really worried about this. If you are, just take some hierarchy of Grothendieck universes, and then you define small with respect to that, and so on. So a prederivator is just a contravariant to functor from this category of small categories to the category of big categories. And by contravariant, I mean contravariant on one morphisms, but not on two morphisms, because there are various ways to be contravariant here, and all used in the literature in different conventions. Then a prederivator is a derivator if it satisfies some axioms, so there is no more structure, it's just properties of these two functor. I will not give you the precise statements of the axioms. I will talk a little bit about this later, but yeah, for the moment you don't need to know that. And a derivator is stable if it is pointed. You can imagine that pointed just means that all the images of the derivator are pointed categories. And then you will have a notion of Cartesian and co-Cartesian squares, and you want one thing to be the opposite of the other. So say that taking a push out is exactly the contrary of taking a pullback. It's a reversible process. And to us, it will just be enough to know that things that we will call strong and stable derivators are the ones that have images that are naturally triangulated categories. Okay, so I will give a bit more detail on this, but I don't think much more. So some examples. Well, the first is a technical one, but we will need this notation at least a lot. So try to remember this. If you have any pre-derivator, D, you take a small category I, and then you can define a new pre-derivator as the derivator D shifted by I that sends a small category J to the old derivator D applied to I times J. Okay. Then this is the main sources of examples for me. If you take any model category, say C, then for any small category I, you can take this class Wi to be the class of those morphisms that are pointwise weak equivalencies on the base on C. And then there is a derivator associated to this that takes any category, any small category I, through the localization of the category of functors with respect to this, this class of weak equivalencies. Of course, I'm not saying that you have necessarily a model structure on this category of functors, but there is work of Cieszynski that allows you to do this anyway with, for example, covibration categories and so on. And the last example, which is very close to the one above, if you have any infinity category C, then there is a pre-derivator that takes a small category I to the homotopy category of this category of diagrams, of coherent diagrams with respect to the nerve of the small category I. And I have to say here pre-derivator in general, because I don't know about the completeness and incompleteness of C, but if C is a bicomplete infinity category, then you always have a strong derivator here, not just a pre-derivator. So some more notions about general derivators. Take a derivator D, then take a natural transformation between two functors between two small categories. And then we will use this upper star notation to denote the images of the derivator. No? So this alpha upper star will be just the image of this natural transformation. So you see it is covariant on these natural transformations, but it becomes contravariant on functors. So this, and functors again are denoted by this U upper star, and they go from the derivator applied to I to the derivator applied to J. Then the left and right adjoints to these upper star functors are, well, they always exist in a derivator by one of the axioms, and they are usually called left and right homotopican extensions. And well, if you take just this I to be the final category, the 1 point category, then you get homotopy limits and colimits in the derivator. And of course, if you take the examples of the model category, of the infinity category, these homotopy extensions or homotopy colimits correspond with the thing you want to. And so about the axiom. So one axiom tells you that homotopic extensions exist, and another important axiom tells you that you can compute them with some nice formulas. And the other are just kind of normalization axioms to avoid very strange things. So more or less this is what we want to know about derivators for the rest of the talk. So this is one other feature of derivators that allows us to build some intuition. Because you see, you really want to think to the objects of the derivator applied to a small category I as I-shaped diagrams. But of course, there is no reason you can do that in general, but at least you can naturally associate one such diagram naturally, functorially, to the objects of D of I. And yeah, the formula is written here, but let me just remark that this is extremely useful to build intuition. So if you cannot draw a picture of the objects of D of I, but you can try to construct an intuition drawing I diagrams on this side here. And okay, so some last notation. Then I will denote by 1 the 1-point category, by 2 the category with just one arrow, with 3 this 3-object category with these 2 arrows. And then I will denote by point the functor that collapses the arrow to a point. And this has 2 adjoints, the one that that takes the unique object in 1 to the 0 here, and the other that takes the unique object to 1. And yeah, of course, this is very trivial, but whenever you apply a derivator to this, you get a very interesting adjoints here. And this is also to justify that also with pre-derivators, I will be able to take this point lower shriek and point lower star, but they do not exist by the axioms, but they exist because they are naturally equivalent to some upper star. So we will use them freely. Okay, so now we know more or less what derivators are, and we start introducing factorization systems, trying to mimic the classical definition. So to mimic the classical definition, first of all, we need to know what morphisms are and what orthogonality of morphisms is. So by morphisms, we will take coherent morphisms, so objects in the derivator applied to the arrow category. And we will say that 2 such objects are coherently orthogonal. We will denote it by this symbol, remembering, reminiscent of orthogonality. If this strange map here is an isomorphism. So as I said before, the diagram functor helps us to construct intuitions. So let us try to draw the diagrams here and see what's happening. So we take a morphism that goes from x1, so from the codomain of x, to the domain of y, and we associate to this sequence of morphisms. Here we have just x, here we have x, here we have 2 copies of a, and here we have y and y. This is the underlying diagram of this thing here. And of course, you see that to say that any morphism from x to y, so any square is of this form for a unique A is exactly the same as saying that any square with this side x and this side y as a unique diagonal. So this strange formalism, if you restrict it to the representable prederivators, that is the ones that are just categories of functors, then this actually gives you back the classical orthogonality. But we can apply it to any prederivator and see what happens. Okay, so let's try. Well, this is just some notation. We define the orthogonal left and right orthogonal of classes in the obvious way. And then we define a prefactorization system on a derivator. So this will be a pair of sub-derivators of these derivators shifted by 2. So of the kind of derivator of arrows, derivator shifted by the arrow category. And then a derivator prefactorization system will just be those such that for any I, for any small category I, you have that this thing here is just this prederivator E applied to I, and this one is the prederivator M applied to I, and so you have this orthogonality and maximality with respect to the orthogonality relation. And then with just this, you can prove most of the properties in this generality, most of the initial properties we had for one categories and for orthogonal factorization systems there. In fact, you can prove that at each level I, the intersection of the two classes consists of isomorphisms. Well, it is exactly the isomorphisms, where by isomorphism here I mean the coherent arrows whose underlying diagram is an isomorphism. Then both are closed under retracts, and you have that the class E is closed under left can extensions, and the class M is closed under right can extensions, so the equivalent for limits and colimits we had before. And if you remember, we had some cancellation laws, and here we have something similar, but not quite the same. But of course, it restricts to exactly the same thing if you go to representable derivators. So we have all these nice properties. And so we can define now factorization systems, which will just be prefactorization systems that have to crumble all the coherent maps. So to make this idea precise, we define a sub-prederivator, this df here, of the original derivator shifted by 3. So, so for example, the things on df of 1 will just be compositions of 2 arrows. Just think, it's just applied to the composition category. And so it is a full subderivator of this d shifted by 3, such that the first of the 2 arrows is in the first category, in E of I, and the second of the 2 arrows is in the second class, in M of I. Then, of course, to say that any coherent morphism is can be coherently factored with respect to this factorization system just means that if I take the restriction of this functor here, which is just taking the composition of the two arrows, this functor here has to be essentially surjective, in the sense that any object here is the image of a factorization here. Okay, so we have a first candidate for the notion of factorization system in derivators. Of course, as I said before, we have all this nice list of properties, but if you remember, we had a second list of properties before, which was the kind of properties related to the fact that E is a correflective subcategory of the arrow category and M is a reflective subcategory. And so you can describe things as algebras over some monad and so on. And we don't have counterexamples, but I strongly believe that you can construct a bad enough derivator such that, and a very bad factorization system in derivator factorization system such that the class E is not coreflective. So this forces us to try another route, which is that of what we called a Functorial factorization system, which are the same thing as orthogonal factorization systems in one category, but they do not need to be the same in derivators in general. Of course, we will see that they will be the same in stable derivators. That is the thing we care of, but in general, we don't know. So we start as before. We take a derivator T, a pair of sub-prederivators of the derivator shifted by 2, and this sub-prederivator of the derivator shifted by 3, which is given by these compositions of maps in the first and second class. Then we take again this psi f to be the composition morphism restricted to this sub-prederivator of D3. And then we say that this f is a functorial derivator factorization system if this functor here is an equivalence of derivators, which just means that it is an equivalence of categories at each level. And okay, in this case, of course, E and M will become automatically co-reflective. But I have to convince you that this has some relation with the properties before. At least a functorial derivator factorization system should be a derivator factorization system. So to see this, I just try to show you how to prove orthogonality of the classes E and M just by the full faithfulness of this psi f. So take an object E in E and an object M in M. And let's try to compute the homomorphisms from one to the other. Then, as we know that this psi is an equivalence, we can take a quasi-inverse phi f. And as it is a quasi-inverse, it is fully faithful. And so we have this isomorphism here. But now we know that E is in this class E, which is coreflective, and so we might, oh, what's happening? Okay, we will have that this phi f of E will have this form you can see here. No, this is the underlying diagram. It will be just the map E here, and then just an equality on the other side. And the same for this phi f of M. It will be something of this sort. And now you can imagine, just by intuition, that a morphism here is just given by a morphism of the centers, which is just this D of E1 M0. And now you would need to see that this isomorphism here is this strange map phi xy that I described at the beginning. But of course it is, because they are all very natural isomorphisms. So you see that with this equivalence, you can recover the orthogonality of the two classes. And well, with a little bit more of work, you can see that they are actually maximal, and that of course they crumble everything, because well, essential surjectivity of course is a feature of equivalences. Okay, so we got our improvement. This is essentially the same as the derivator factorization system we had before, but with these two co-reflective and reflective sub-derivators of D. Okay. So now that we have these classes orthogonal, co-reflective and reflective, we can try to generalize, try to extend all the rest of the theory we had in one categories. So we start with the functorial derivative factorization system F, and we take these inverse equivalencies from, of course, there is a mistake here. This shouldn't be a D3. This is a full sub-derivator of that, but it is dF. Sorry for that. So we take this, and then in fact, one can compose this phi f here with evaluation at the central object to get this morphism of derivators ff from the derivator shifted by 2 to d. And in fact, even if this seems to lose a lot of information when compared to this phi f here, if you are creative enough, you can find a construction that completely reconstructs this phi f here from this ff here. So all the information we had here, all the information about f is given by this psi f, but then it is recovered by its quasi-inverse, and then it is recovered by this. So you have bijection between these kind of things. And you can call a normal factorization pre-algebra. We will be clear later why we do that. A functor of this kind that goes from the derivator shifted by 2 to the derivator itself, such that it sends identity morphisms to the objects of which they are identities, as in the one categorical case. And then one can really characterize those functors with this property that come from some functorial derivator factorization system. And well, there is a very explicit characterization I had no time to give you, but we call these Eilenberg-Moore algebras by analogy. But in fact, we can consider the two categories of all pre-derivators, which is given then, well, the objects are just the pre-derivators, so two functors from small categories to big categories. Then you have pseudo-natural transformations, and then you have modifications among them. So this is a two category, and you can define a squaring monad on this pre-derivator two category, which just acts as this shift functor I described at the beginning, and where these other two things are just, well, delta is just the diagonal of the square, and then we apply the derivator to that, and this is just the usual point functor that we have seen many times. So you can see that this is a strict pseudo monad over this strict two category. And in fact, for any derivator d, the following are equivalent for a normal factorization pre-algebra f. That is, f can be given the structure of an algebra over this, where by an algebra I mean a lax algebra over this strict pseudo-monad, but I will just say algebra and monad to avoid my mistakes in recalling the too much precision, and that there is an isomorphism like this. So this is a bit less than this because you don't ask coherencies and so on. And that f is an Eilenberg-Moore factorization. So the ones coming from functorial derivator factorization system. So you see that the functorial derivator factorization systems can then be seen as monads, as algebras for this squaring monad, exactly as we saw for the one categorical case. Okay, so we have now these two definitions, the one done kind of pointwise, seeing orthogonalities, and this one seeing this, say, global behavior, no? This big equivalence of two derivators. And we don't know if these two things are equivalent in general, but if we restrict to stable derivators, so strong and stable for us, so the ones that have triangulated images, then the two things are always the same. So all the derivator factorization systems defined by the initial orthogonality relation are functorial. And yeah, the proof of this is not very difficult. We just need to construct suitable to complete. You remember in the definition of orthogonality, we have these units and co-units, and then you have just to complete those two triangles, take some long exact sequences associated to that, and then you just do some homological algebra in there. And so there is nothing deep, it's just a homological algebra going on here. And in this setting, not only all derivator factorization systems are functorial, but we can even reinterpret the orthogonality relation that we introduced at first. So just take two coherent maps at some level of the derivator and consider this triangle here. So this, I hope I had written the underlying diagram. So this triangle just takes coherent morphism X. It sends it to the identity of X1, and then it sends it to the map that goes from the cone of X to 0, and then you take the shift. So you can always construct a triangle like this. And then if you apply the contravariant Hom functor represented by the second object you have, Y, you get a long exact sequence like this, where the map 2 that appears here is exactly the map that we use in the definition of orthogonality, in the sense that X is orthogonal to Y by definition, if and only if 2 is an isomorphism. But then, as this is a long exact sequence, you can see that 2 is bijective if and only if this map 1 here is the 0 map, and the map 3 here is injective. So what do we gain about doing this? Well, if you see, both the map 1 and the map 3 just involve objects that are at the base of the derivator, that are in D1. We are not in D2. So it is really saying that the orthogonality of two coherent arrows just depends on conditions you can see on the underlying diagrams, because they just depend on x1, y0, the cone, which can be constructed up to isomorphism just from the underlying map. And so this suggests that for any triangulated category, because these things, you don't have any way to construct this isomorphism 2 in an arbitrary non-enhanced triangulated category, because you don't know what D of 2 is. But you can try to mimic these two conditions, 1 and 3. And so you can try to get this. Take it now a very general triangulated category. You are not supposing any kind of enhancement for T. Then you take two maps in this triangulated category, and you complete those two triangles. Then you say that the map E, the first one, is orthogonal, is left homotopy orthogonal to the second one, if exactly the two conditions that we had before. This map here, which is the obvious one, is trivial, and this map here, which is the unique you can imagine, if you try to work this out a little bit, this has to be injective. So this gives some kind of triangulated orthogonality relation, and you can use that to define triangulated factorization systems in any triangulated category in the obvious way. There's just one point that you have to add. You have to ask that the class E is closed under shifts, or the class M is closed under negative shifts, because this will not be automatic if you just stick to the base, but just because if you think for derivators, this becomes automatic, but just because you can prove that the class E is closed under left can extensions, and this is in a particular instance of that, and in a triangulated category, you don't have homotopy can extensions in general, so you have to add it manually. But now, think for a moment to the case of one categories. If you have a factorization system on the category, you can lift it to all the functor categories, and these liftings, pointwise liftings, will just give you a factorization system in the associated pre-derivators. And you can actually prove that this is the unique way to do that, in the sense that you cannot have two different factorizations, pre-derivator factorization systems that have the same restrictions to the original category. There is a unique way to lift them, and that is the lifting pointwise. So we can now ask, take a strong and stable derivator. So you know that the base of the derivator, so d applied to 1, is a triangulated category, and you can take a triangulated factorization system in that triangulated category there. So you may ask, is it possible to construct a lifting for this thing on the base to the wall derivator? So a derivator factorization system, which is the same of a Functorial, in this case, derivator factorization system, such that on the base it is this thing here? Well, the answer is yes. This is a very difficult theorem to prove, but the answer is yes. And in fact, the liftings are very easy to describe. It is very difficult to prove that they give a factorization system, but they are very easy to describe. They are just pointwise liftings of the thing you have on the base. And you can even see that this is the unique possibility to lift this triangulated factorization system on the base. So you have this uniqueness of liftings. And to conclude, I guess, how much time do I have? Do I have 5 minutes, more or less?
Of course you have 5 minutes. Yes,
okay.
yes.
Yes, nice. So just to conclude, I would like to mention a connection with infinity categorical factorization systems, because there is a well-established theory of factorization system in infinity categories. And so one may ask, as we have seen before, that for any sufficiently bicomplete infinity category, you have an associated derivator. You can imagine that if the infinity category is stable, then your associated derivator will be strong and stable. Then you can ask if the factorization system you have on a presentation of the infinity category are somehow in bijection or can be recovered from these derivator factorization system that somehow belong to the homotopy categories of the infinity category. And well, of course, in general, I don't think that will be true, but you can do it in stable categories. And if you have some familiarity with chapter 2 of Higher algebra, you may remember that in the part where Lurie talks about T structures, he proves that a T structure in the infinity categorical sense, so these reflection and correflections that are with the properties of a T structure, but on the presentation, are the same as the usual T structures in the sense of triangulated categories on the homotopy category. So that T structures are really determined by the homotopy category. So here we extend that result not just for T structure, but for all factorization systems on a stable infinity category. So let me remind you what infinity categorical factorization systems are. So take C is now an infinity category, and take two edges F and G, and then an element Q of this morphism group will just be a square, such that on one side you have F, and on the other side you have G. So this kind of commutative square that has F and G on both sides, what are used to. And then you define a filler to be a diagonal for this square, which means that not a strict diagonal, but a diagonal up to homotopy, say, up to these two homotopies. Then you say that our edge F is orthogonal to G if the space of fillers is contractible, so what you probably expect. So if you take two subclasses of the one simplices, then this is a factorization system if these two classes are orthogonal and maximal with respect to this orthogonality that we have defined here. And if any other one simplex can be written as a composition, say up to a homotopy, the usual sense of infinity categories, or if you want just passing to the homotopy category of things from E and things from N. Okay. Then you can prove that if C is a bicomplete stable infinity category, and if you take DC to be the induced derivator, induced strong and stable derivator, then you actually have a bijective correspondence from factorization systems in the infinity category and the derivator factorization systems we define here on the homotopy level. And let me just comment on this bicomplete here. That just depends on the fact that we are choosing to take all the small categories here as the domain of our derivator. But of course, you have a lot of variations of derivators, for example, done just for finite ordinals or things like that. And you can change, the theorem remains true also for those cases. So you can just take C just any stable infinity category, which means stable means here, so finitely bicomplete, and take here something defined over some for example, some finite categories, I mean direct finite categories, and then you will have again this bijection here without assuming bicompleteness. And if I have a couple of minutes more, I will just conclude with a nice picture that is exactly what I hoped for when I started this project. And so, roughly speaking, I will not be very precise here, but roughly speaking, take a factorization system in any of the settings we have seen in one categories, in infinity categories, or in pre-derivators, or even if you want the triangulated factorization system we have seen, then we say that this is a torsion theory if both classes have the 2 out of 3 property. Of course, it's a bit technical to say that it satisfies the 2 out of 3 property in P there, but it's just a matter of language. So you can imagine what I want to have. So furthermore, you say that a factorization system is left normal if whenever you take an object X and you take the factorization of the final map from X to 0, so like here I think probably some pointed situation, but you can do it just with the terminal object. And you take this factorization here, and then you take this homotopy pullback square, where you take just this map E here that appears here, and the initial map of this object that stands here in the middle. You take the pullback, then you want that the final map, starting from this pullback here to the terminal object, is in the class E. This is a technical thing, but it is very useful to us. Of course, right normality is defined dually, taking initial maps and the Puschel square. And you say that a normal factorization system is something that is right and left normal. Of course, you need that in most situations. Of course, if you are in a stable situation, then right will be equal to left, which will be equal to sided normal, just because push-outs and pullbacks become the same thing in there. Well, not the same thing, but push-out squares and pullback squares become the same kind of squares. And then let's start with the pointed derivator and consider the family of all normal torsion theories in this sense here. Then, if the derivator is strong and stable, this thing is in bijection with the T structures on the base of the derivator, on the triangulated category D1. But if instead the derivator is representable, so discrete, it is C to the power I for all I, and abelian, meaning that the base is abelian, and so equivalent to all the other categories are abelian, then this same class here of normal torsion theories corresponds to torsion pairs on D of 1 and torsion pairs in the classical sense of Dixon, say in abelian categories. So this is a very nice result, I think, just because it tells you that from the point of view of factorization systems, these structures are exactly the same as torsion pairs in abelian categories. And so all the analogies you usually see, well, they are there because they are exactly the same thing for some point of view. Okay, I think this is all I wanted to say.
Okay, thank you very much, Simone. And now we are open. Okay, we thank the speaker again. We have silent applause, so thank you, Simone. And now we are open to questions. So if someone wants to ask a question, that's a good moment to do so.
I have a couple of comments I would like to make, if I may. So, of course, I join Ivan in thanking Simone for the nice talk. Can you go back to the slides on factorization systems for infinity categories, please?
Oh, yeah.
Yeah, this one here. Yeah, so I don't think that the notion of filler is the correct one there, because what you actually want is a filler which is homotopically coherent. So you have a square Q, and here you have a diagonal, and you fill the two simplices of the square. And that's it with this definition. But what you actually want is an extension to the 3 simplex. So yeah, delta 3 is the square with a diagonal filler.
Yeah, I think I've copied this definition just from Luri, but I may be wrong.
Yeah, I mean, it's just a comment that is not enough to be a filler. Yeah,
okay. Yeah, I see what you mean. It's not coherently filling.
Right, because yeah, exactly. And another thing is, I think you said, but I'm not sure if I got it correctly, that you don't know, or maybe even that it is false, that your notion of factorization system agrees with the infinity categorical one in general. Did you say that, or am I just mistaken?
I said that I mean, of course it coincides when the infinity category is actually a 1 category and if it is stable, but yeah, I think they may not coincide in general.
And so you suspect that they do not coincide?
No, and the fact will be, you see, when we take the orthogonality relation, we just ask for an isomorphism of abelian groups. If you take some enrichment of derivators in some category of spaces, and then you ask for equivalencies of the spaces now of homomorphisms, then probably you will have the same notion. But as in the stable case, then you can always take just the truncation to level 1, then they become equivalent. I'm not able to construct an example as bad as to show that this is the case, but the intuition is that you will miss some coherence in the cases that are not stable or discrete, the 2 extremes.
So, but in particular, sorry.
No, but it's just intuition. I don't have any example. I would be happy to be wrong on this, of course.
So in particular, you don't have a, because I struggle a little bit to follow the derivator notation. So maybe you said this, and yeah. I apologize if this is the case. But in particular, you don't have a description of factorization systems in terms of, let's say, something that is similar to the slide that you're on right now. So something in terms of mapping spaces and having something that it's a homotopy pullback. So the usual thing that you do for like ordinary categories or even infinity categories, it works even in that context for orthogonality and so on. I assume that based on what you said, you don't know if that's available. Otherwise, it would be clearly equivalent.
Yeah, no, I don't think that it's easy to construct in general for a general derivator. Probably considering some enrichment over spaces, you can try to do something of that kind. But even in that case, it's kind of complicated because you see, if you take a couple of objects at some level of the derivator and you have morphism between these two, you don't have any grasp on that. This is just a morphism in a category. You don't, I don't know how to explain this, but yeah, infinity categories are a much stronger language in general. So I don't know in the end how much stronger, but it is much more expressive at least. It makes these characterizations possible and easy, and with derivators you have to struggle a little bit more.
Okay, thanks.
So I would not know even how to guess something like this. I mean, let alone prove it, but I would not know what to guess.
If I understand well your question, Eduardo, this is genuinely two-dimensional or even higher dimensional. The problem with derivators is that everything is engineered to work by just with one categorical properties with some isomorphism, some coherences sprinkled over. I don't think this definition is suited for the generalization that you asked for. I also don't think this is the very, as you might have noticed, there are many acts here and there to make things work. So this is probably a definition that in the setting of derivators, it's possible to refine a little bit. And probably the right notion will turn into being equivalent to the one for infinity categories, at least at the stable level. You see the problem, everything we say work in...
Well, at the stable level, they are already equivalent.
Yes, yeah.
Yeah.
Unstably, the problem is that you cannot have, let's say, this is probably another consequence of the fact that there is no canonical enrichment for derivators over spaces as there is over spectra for stable derivators.
Well, I think that there is something that can be done there, but yeah, they are all...
You see, but you see, this is, at least from my point of view, this is what motivated me to look into the two category theory of derivators, just not the one category theory alone. Because you see, you would really like to define the orthogonality property over a pseudo-algebra for the squaring monad in a more canonical way. But at the moment, we have no idea how to do that.
Yeah, and to take limits or co-limits, say homotopy limits or homotopy co-limits or systems of derivators, things that you do all the time in infinity categories, but you cannot do in derivators for the moment.
Like one good thing would be, once you have factorization systems, you would like to have a tool for inducing them. And there is no other way to do that than the small object argument. But what is a transfinite construction in derivators? No one knows. At least I don't know. We don't know.
Yeah, I mean, from my point of view, derivator, one shouldn't try to have all the results that one has in other models of higher categories in derivators. But when one can have something in derivators, then it is a very useful concept, because it means that, of course, it is below any other, it is kind of, I mean, it does not depend on any model of higher category theory just because it is on the level of homotopy categories. So if you can do things there, it is much more, I mean, I like it a lot more. But probably there is no point in trying to pursue derivators as far as infinity categories have arrived. I don't know. I don't think so. It is just a refined theory of the homotopy category, and that remembers a lot more than the usual homotopy category. The homotopy derivator just remembers a lot more, and then you can prove things already there.
I'm sorry, I have to stop here the discussion. We can continue after we close the seminar for everyone. People can stay, and so there is no problem. The discussion can continue in a